In this problem, we're looking at an adiabatic turbine that we expand an ideal gas through, and we do this at steady state. And what we want to know is the outlet temperature and the work done. So let's pause and look at a diagram of the process. So I've indicated the unknowns. The outlet temperature we'll call T2, and the work and adiabatic. So Q is 0. The heat capacity 31 joules per mole Kelvin. Since it's reversible and adiabatic, we can use the relation between temperature and pressure. Remember, this relation is good for a steady state flow system or a closed adiabatic reversible process, where the pressure ratio is raised to the power of the ideal gas constant divided by the heat capacity. So I'm going to, again, pause, substitute the numbers into this equation. So I've had to convert the temperature, of course, to absolute temperature, so 450 plus 273. And then the ideal gas constant in units of joules per mole Kelvin is 8.314. So now I can calculate the outlet temperature. So the outlet temperature, 284 Kelvin, 11 degrees centigrade. I can now use the first law for a steady state flow system, and that's delta H. So delta H is Q plus W. Q is 0. Ideal gas delta H is Cp delta T, which is 31 joules per mole Kelvin. The final temperature minus the initial temperature in Kelvin gives me a value for work of 13,609 joules per mole, which I'll write as 13.6 kilojoules per mole. So we've calculated the work, and I should point out this is a negative sign because the number here is negative and this is a negative sign. Of course, it's negative because we're removing energy from the system as work.